Okay, in this video we're going to talk about exponential functions. So exponential functions are important. We're going to see them in a lot of real life circumstances, so they can model a lot of different experiences, whether or not it be carbon decay or whether or not it be a isotope breaking down that is not carbon. We could look at something that is radioactive, for example. We could also look at the way that annuities are calculated and the way that we see credit card rates impact how much we owe. So all of these are example of exponential growth and decay models. So it's important that we understand our exponential function. So let's go ahead and define an exponential function here as a value of a raised to the x. And we're going to state here that a is greater than 1. So an example that we could look at would be 2 to the x. 2 to the x is a great example. So, and notice here our base is positive. So if I go ahead and just graph this, I'm going to graph this pretty quickly just to show you what this looks like, is that, remember, with our base a raised to x, if I want to find f of 0, everywhere I see an x in my function, I replace with 0. We know based off of our exponent properties that anything raised to 0 is always 1. So the nice thing about these is that we know our exponential functions in this form will always intersect the y-axis at 1. So we know our y-intercept is going to be equal to 1. So we think to ourselves, and back in those exponent properties that we just discussed, can we raise 2 to, for example, can we raise this to any value that equals to 0? And we think, okay, let's think. 2 to the 0, that gives you 1, so that's definitely a no. Let's try 2 to the negative 1. 2 to the negative 1 is really 1 over 2 to the positive 1. Remember, we take the negative exponent and we can make it positive by bringing it down. So 2 to the negative 1 power is really the same thing as me saying 1/2. So, okay, as I'm doing a t-chart here, let's go ahead and do a t-chart. If I do a t-chart of x and then I'll do f of x, when x is 0, we get a value of 1. When x is negative 1, we get a value of 1/2. Okay, let's try negative 2. Okay, let's see. 2 to the negative 2 power. This gives us 1 over 2 to the positive 2 power, which is a value of 1/4. Okay, I see it's getting smaller. As I get more negative, it's getting smaller and smaller at an exponential rate. Let's try the positive way. Let's try positive 1. So positive 1, I know that's just going to be a value of 2. I plug that in. I'll plug that in over here. So I get 2 to the first power, I get a value of 2. Let's try a value of 2. This gives me 2 squared, and this gives me a value of 4. So I'm getting more and more, I'm getting larger. I'm getting positive and larger. So when I get a negative value, I get smaller. So let's slide 2 to the negative 3 power. This is 1 over 2 to the third power, and that's going to be a value of 2 times 2 is 4 times 2 is 8. So I am getting even smaller with each time I take a step to the left in the negative direction. So notice here at negative 1, at negative 2, at negative 3, I'm getting smaller and smaller and smaller. And as I keep going in the positive direction, I'm getting larger and larger and larger. So ultimately, my graph will look something like this. And it will shoot on out like such. So that's an example of a to the x. It's going to be very, very close to the x-axis. But notice, there is no value here. There is no value here that ever equals to 0. So we say that we have a horizontal asymptote at the x-axis. And we can say the x-axis and define that in terms of a line y equals to 0. And that's not g equals to 0. It's y equals to 0. So we have a horizontal asymptote. So I'm going to designate that with a dotted line here that exists like such. So if we have a horizontal asymptote there, that helps us describe the range. So in this example of a to the x, I want to make sure to describe the domain. So in here we have to describe the domain, and we see that I have these arrows pointing out to negative infinity, and it goes all the way to positive infinity. So the domain of a to the x is going to be all real numbers, denoted negative infinity, positive infinity, or in set notation as x existing as all real numbers. However, the range is going to be slightly different. Remember, we read the range going from the bottom of the graph to the top. So we recognize that it starts at approximately 0, but it never touches 0 because we have an asymptote. So we recognize that we start at 0, and we're going to represent that it starts but never touches with an open set of parentheses, and then it continues on to positive infinity. It goes on to infinity and beyond. So we go from 0 to infinity, and we can represent that in set notation as a set of y such that y is greater than 0. So these exponential functions have very consistent properties in regards to their domains and ranges. All of the transformations that I've discussed prior will hold true in these exponent functions as well, these exponential functions as well. So what happens as a gets larger? So let's go ahead and say what happens as a gets larger. So let's go ahead and look at a couple examples. Let's say we have f of x equals 2 to the x. Let's say in purple we have g of x equals 3 to the x. And let's say in blue we have h of x, and this equals to a value of 4 to the x. So let's see what happens as the base gets larger and larger. What happens? So 2 to the x, we know it's going to start off here, and it's going to have to intersect at 0, 1, and it's going to shoot on up like this and become exponential. And well, it's always exponential, but it exponentially increases. And it will always intersect 0, 1. Let's look at the second function. Let's look at 3 to the x. It's slightly larger than 2, so we're still going to be down here, and it pretty much overlaps all the way up until we get to 0, 1. But then it becomes more positive quickly, It becomes positive quicker. So it extends up faster. All of a sudden we think 3 squared is 9 and 3 to the third power is 27. It becomes more positive more quickly. So I hope that's the correct grammar. So as we keep going, over in this area, we don't really see a very large change. However, where we see a large change is going to be over here. It's going to be a very, very large change over on the right side of the y-axis. So now let's go ahead and see what happens. Let's see what happens here with 4 to the x. So let's look at 4 to the x. So this over here, don't see any relative difference here, but then as I hit the y-intercept, it now is going to become more steep. So that base, as that base increases, the curve becomes more steep after it intersects the y-intercept. So keep that in mind. As the base gets larger, the graph becomes steeper and it escalates more quickly. So let's talk about what happens. Let's talk about what happens when our base is negative. So let's go ahead and talk about what happens when our base is negative. So let's go ahead and look at f of x equals negative a to the x. So in essence, we're negating our function. So as we want to, we can do a t-chart to help us give an idea. So here we have x, we have y. So if we look at f of 0, this gives us negative a to the 0. And be careful, ladies and gentlemen, this gives us a value of negative 1. This one's a little different. So when x is 0, y is negative 1. Let's try f of 1. We get negative a to the first power, so this would give us a value of negative a. Okay, that seems a little weird. Let's substitute this value in for an example like f of negative 2. Let's try f of x being equal to negative 2 to the x power. So if we look at f of 1 here, this gives us negative 2. So this gives me a better understanding of what's going on here. So I have negative 2 to the first power, so that doesn't change. I'm really content there. So let's try here at 2. So we're going to have f of 2 equal to negative 2 to the second power. This gives us negative 4. Okay, so I see something that's happening here. I'm seeing my trend. And hopefully remember what happens when we negate our function. So remember that little rule back with our transformations, that if f of x equals to the negation of f of x, we rotate about the y-axis. So what happens here is that we take our original function, which looks something like this, and we rotate it about this axis, so now it's going to become a mirror image and flip on down like this. So this right here would have been f of x equals a to the x. This guy right here is f of x equals negative a equals negative a to the x power. So this will change by rotating about the x-axis. So we have to be very careful if we have this negative coefficient, a -1 or -2 and -3 and so forth. It will cause it to rotate about the x-axis. So let's look at the domain here. The domain will not change. The domain will not change. It will still exist from -infinity to +infinity, also known as all real numbers. However, I still expect that same asymptote to occur along the x-axis because we can never raise a base to ever give us a value of 0. So our range starts down at -infinity. It starts at -infinity and goes to 0, but it never ever touches. So it gets very, very close, but never ever touches. So keep that in mind. So now in the last portion of this, I want to discuss what happens when we have a negative exponent. So let's go ahead and discuss f of x equals a to the negative x power. So what happens when we have a negative exponent? This is slightly different, and we start thinking, okay, it must flip to. No. It does not flip along the x-axis. It actually flips along the y-axis. And let's talk about y. So remember, if I have f of x equals 2 to the negative x power, if I want to make this exponent positive, I can bring it down to the denominator, and I make it positive. So here, this is the same thing as me saying 1 over a to the positive x power. But remember that little trick we learned in our transformation section. If we have f of x equals f of negative x, so we negate the x variable, this will give us a rotation about the y-axis. A rotation about the y-axis. So let's go ahead and see what happens, and we'll do this in white, the graph in white. So in purple, I'm going to go ahead, I'm going to go ahead and denote a to the negative x, and then in white, over here, I'm going to denote a to the positive x. So we know a to the positive x looks like such. It's going to get very, very close to the x-axis, and it's going to hit 0, 1, and shoot on up. So it's going to hit this value at 0, 1, and shoot on up. However, if we rotate about the y-axis, it's going to do the opposite. It's going to start, well, it's going to actually start here coming from the left, but I draw it easier coming from the right. That's just the way I think. So it's going to come over here. It still intersects and shoots on up like that. So hopefully you guys can see the symmetry. You guys can see the symmetry that exists. Not necessarily, okay, not symmetry, I don't mean symmetry. You can see what happens when you rotate it about the y-axis. I used the wrong word there. So this right here is going to be a to the negative x, and this right here is a to the positive x. So in this circumstance, this is exponential. This would be an example of exponential decay, where something decays at an exponential rate. And this is an example of exponential growth, where something grows at an exponential rate. So a very, very common example of exponential growth, you would think my paycheck, and that is not true. But actually, a very common example is a bacterial or viral colony. These are examples of exponential growth, and a lot of populations model exponential growth. The most common type of exponential decay that we're probably going to see is we're probably going to think of radioactive or isotope decay. That's an example. So carbon-13 is very, very common. Also, your radioactive elements like uranium and plutonium, they're going to talk about that as well. So start thinking to yourself, whenever you see exponential growth and decay functions, the way that their graphs are modeled. It will help you work through your problems.